It's good to see we consistently have about a dozen to 20 people watching the live stream as we are streaming it, and then at least a similar number of people watching it again after the fact. So this is apparently a very good medium to use for people who are either not attending or having problems with the English language.
You never know, there might be just some random YouTubers looking for some viral content from us.
Well, it's small number statistics, I'm sure there's a few, but we will see.
I'm just going to share my screen in preparation.
Okay.
Because everyone will see my screen otherwise.
We have a few more minutes to go, so.
Yeah. Okay.
You're good.
That shows everything, right?
Yeah.
And doesn't show my own face on the top right of the screen.
For me, it doesn't, but I have split windows, so it might for other people who are participants.
Me neither. For me neither, and I just have the laptop.
Okay.
Okay. My video is on, so it should work.
I can log in as a participant and see if that's.
Okay. Because it's nice to look my audience in the eyes.
The Zoom number. Yeah, as a participant, you see your slide with a little box on the top right with the video.
Okay, cool.
And I think now you can also change the view, so the video falls outside the screen. At least on the top right, I see another option for that.
Oh, yeah, it makes a difference for me if I have the full screen or...
Yeah, only on the full screen, I think.
Okay. And it goes to like a separate split screen, right? So,
exactly. And you can regularize the size.
Let's see.
Yeah, people are trickling in. Give them a couple of minutes to join the webinar session.
So you can't see the bar of the four of you on the side of my screen?
No.
Okay, cool.
Lots of discussion still going on Mattermost. Numbers are rapidly increasing, so okay. I think we've reached quorum. Good day, everybody. We are on the second half of day 3 with the CASA workshop, and this afternoon we've got one lecture and then our social event, which is the walk. And the lecture this afternoon is by Jack Radcliffe, who will present on the wide field imaging specifics of CASA-VLBI data processing. So go ahead, Jack.
Cool, thanks, Ilse. Yeah, it's great to talk to everyone, even if it's not in person. I'll give a shout out to everyone in YouTube who's watching as well. So this afternoon I'm going to talk about wide field imaging. It's a little bit different to what we had before because, well, as you'll see, a lot of this actually isn't part of CASA just yet, and is kind of a very big kind of area of research just at the moment. I'm from the University of Pretoria, so greetings from South Africa, and if you have questions on this, then please put them in the Madamaze channel, or you can email me later on as well if needs be. So this is kind of our motivation. So I'm going to do a little bit of science, which haven't really been done before in these talks. So why would you ever want to image the degrees of the sky with VLBI? And then I'm going to talk a bit about the challenges that come up when we want to do wide field imaging, and then followed on by a bit about the, how we calibrate wide field VLBI data. And in particular, there's kind of three aspects which are a little bit different to your standard calibration. That's the phase referencing, your self-calibration, and also, as I'll talk about for almost 10 slides, will be how we do primary beam correction. And then I'll finish with some conclusions and takeaway points. But the key thing with this talk as well, for those who, only care about their source in the center of the field and, might just be going to watch the US elections instead, is I'm going to try and show you how some of the techniques that we do for wide field observing might be applicable to your observing just this tiny, couple of arc seconds in the center of your field. So let me begin. So this is kind of just, what do we mean by wide field VLBI? And this is, well, for those who don't do much radio astronomy or has just started, this is just simply concerned with imaging the entire primary beam of an array. And the primary beam, as you should know from Radio Astronomy 101, is effectively your directionality of your telescopes, or the gain, or in a non-technical term, just your effective sensitivity as a function of your sky coordinates. Now, the key thing about using VLBI is that you can now see multiple science targets in a single observation. And on the right-hand side here, we've got a lovely JVLA plus Merlin image of the Goods North Deep Field, and you can see multiple sources being shown, and then as you get to the edge of the primary beam, the noise increases because you're effectively less sensitive there. Now, historically, this is much easier for shorter baseline instruments, and lots of the problems that come with wide field imaging have been solved for shorter baseline instruments. But with VLBI, you've kind of got a unique way of looking at many different phenomena that you wouldn't see in your arc-second scale resolution instruments. So here's some kind of science examples. So there's, the classic supermassive black hole binary issue where, these are important to galaxy formation theories, etc. There's this wasn't from a wide field VLBI survey by Roger Dean in 2014, but is a Nature paper of a triple supermassive black hole. But then in the Cosmos VLBA survey by Noela Herrera Ruiz in 2017, they saw two candidate supermassive black hole binaries. If you're looking at this with your VLA telescope, this would just be a single boring blob, and you wouldn't know what's happening underneath the flux. And even in our Goods North survey, we've got a candidate supermassive black hole binary, where you can see in the background on the right-hand side is the HST near infrared with two optical peaks, and we have two VLBI detections in this object. So this is just one of the many things. We've also got, these beautiful gravitational lenses, which Christiana is pivotal in bringing out, and this is our, our mascot for our conference. And these things are rare, but the high resolution VLBI can constrain your lens models, give you probing of kind of low mass end of the dark matter halo mass function. This is important in how, dark matter grows in the universe. But you can only see this again using VLBI, at least on these sort of scales. And indeed, Christiana in 2019, she searched 3,640 MJIVE 20 sources, which is a wide field VLBI survey of the following the first VLA catalog, and found two gravitational lenses in there. So, if you get a statistical sample of these things, you can, probe cosmology and much more using the high resolution afforded by VLBI. Now, at least to date, most of the work has been done on AGN surveys. So Edo Middelberg and Noela Herrera-Ruiz and myself have been working on this for almost 10 years now. I haven't. And, you know, VLBI is a kind of a sure indicator of AGN activity. You have high brightness temperatures, so at high redshifts, you get, it's most likely going to be from an AGN. And then you can use VLBI detections then to try and understand the nature of radio-made AGN, feedback, et cetera, On top of this, you know, we can find that, you know, other AGN identification methods, so far infrared X-rays, are sometimes incomplete or contaminated by star-forming galaxies. Now, this is just kind of a taster of the things you wanted to do with, you can do with wide-field VLBI, but there's many, many other use cases. So if you guys out there are thinking, oh, this could be useful for my science, then put in a proposal, and you can get some nice wide-field VLBI data. And I'm going to show you how, you know, you can calibrate it and how easy it is nowadays. It used to be quite difficult. So, you know, we've got to look at what are the challenges of imaging the entire primary beam. And the first one is just the sheer image size. So let's us assume, you know, a 0.5 degree field of view, which is, you know, a 25-meter telescope at 1.4 gigahertz approximately. And you Nyquist sample your restoring beam by three times the Gaussian width of the restoring beam. And if you wanted to do this for the VLA, or the Very Large Array, in the A configuration, so you're looking at 32 kilometer baselines, which gives you 1.4 arc-second resolution, you're looking at, you know, an image which is 1.4 times 10 to the 7 pixels, which is about 4,000 on the size. And, you know, this is doable with modern day computers, but if you then go to the very long baseline array with the same antennas, 25 meters, 1.4 gigahertz, but now you have a 6 milliarc-second resolution, you're looking at something in excess of 1 times 10 to the 11 pixels to try and image. And there isn't many computers in the world that would be able to make a 300,000 by 300,000 image. Not that I know of anyway. Please put them in the chat if you know of one that can do that, because I'll be very interested. The second issue that you have is smearing. So, you know, as Ivan said yesterday with the equation, you just need a little bit of time averaging and a little bit of frequency averaging to get this smearing effect, drastically constraining your field of view. And this effect is more prevalent when you have long baselines or when you're going far away from your primary beam. And you guys can think of it as kind of a breakdown of our radio interferometer measurement equation. So, you know, we have to average over time and frequency in the radio interferometer measurement equation. And when we, for example, do it in frequency space, the assumption of a monochromatic source breaks down. And this occurs much worse when we get to the edge of the primary beam. So on the left here, we've got the MVSS of two sources. This one's at our phase tracking center, and this one's far away towards the edge of the emerling primary beam. And you can see that, you know, the source structure looks okay. It looks fairly, you know, normal, I guess. But when we go to emerling, which has longer baselines, at the center of the primary beam, we don't have this smearing effect. The source looks okay with a nice jet shape, double-sided jet. But when we get to this source, which is just a point source in the VLA, you know, this is massively smeared. It looks kind of like a meteorite. And this is just wrong. And as Ivan said, this is just a convolutional effect, which is smeared your imaging. So this is another effect that's the issue with doing this. And then the final effect, of course, is what we call the non-coplanarity term, or the W term. People who have done wide field VLA or unconnected interferometers will have, you know, despised this term. And, you know, if we look at the ideal radio interferometer equation up here, you know, if we want to do the 2D Fourier transform, we need to somehow get rid of this W term. And when you have either large L or large M, so you're making large images, this W term over here is non-negligible. But also this W term essentially tells you whether you can approximate your interferometer on a 2D plane. That's one way to kind of think about it. And when you have VLBI interferometers, which are on the other side of the world, this W term is also going to be quite large. So this makes it much more difficult to image. And you can see in this image here, we've got a emailing source, which is 7.5 arc minutes from our pointing center. And on the left-hand side, we've essentially used the W projection algorithm to fix for this W term over here. So we take this into account, and you can see that we've kind of got something that looks like a source. There's some calibration errors, but don't worry about those. But this, this projection is computationally expensive. And if you didn't use W projection, we end up with this weird ring smeared shape. Our peak flux is reduced, and we end up with this weird hole in the center. And no, this is not what the EHT did to get their black hole image. But the key thing of this is that the severity of these issues is essentially proportional to your baseline length, well, not exactly proportional, and your distance from the phase center. So they just get worse as you go further away. So how do we get around this? What are our solutions to this? So one of them is to do a standard wide field correlation when you do the VLA or emailing. This is the standard way of doing it. And all that you do is you correlate at some very, very high temporal and frequency resolution, which then restrains your smearing. Remember Ivan's equation, if you do less averaging, then you end up with a much larger field of view. And so here on the right-hand side, for example, we've got an example wide field VLBI survey I want to do of M82. There's a nice optical image, the only optical image I've ever made in my life. And the yellow circle on the outside is just the half power beam width of the EVN, or of the Effelsberg and Lovell telescopes combined. And by doing the correlation at very high in temporal and frequency resolution, we end up with some field of view due to our smearing. And you normally select this to be, I only want 10% smearing or something like that. That's typical. But the result that you get from this correlation is you end up with one huge monolithic data set. And because VLBI sources are few and far between, this is going to be 99.999% noise. And on top of this, the averaging is a kind of play up between how big do you want your data to be and how accurate do you want your imaging to be. And so this huge single data set is going to often be terabytes in size, and at least when this was first conceived with apes, which used a single core, this was not feasible. And often on top of this, you have to, if you want to shift to other positions in the primary beam, the standard software is just simply not accurate enough to be able to shift and retain your astrometry that you need. And just to kind of highlight this a little bit more is that if you take a 12 telescope 12-hour EVN observation at 1 gigabit per second, you're looking at kind of in excess of 15 terabyte single data set. And unless you're doing LOFAR, you're not going to be able to reduce that. So the second way, which was conceived by John Morgan, Adam Della, and Art Kimpema, I never say his name right, but he's been helping you with the Jupyter notebooks, is this method of multiple phase center correlation. Okay, and this works slightly differently to our standard correlation. And this way of correlating instead splits our data into time chunks. So here's our time chunk, a little time chunk of data, which then you correlate or do an initial pass at very, very high time and frequency resolution, which restrains your smearing to the edge of the primary beam. Now, what you then do, and this is highly parallelizable, is you then copy this data set once correlated and phase shift using an accurate phase rotation to multiple locations in your primary beam. So now, we set these positions so they can cover, for example, our M82, and we're not looking at just noise over here and things like this. And then on top of this, you then average down those data sets, which are now being phase rotated in time and frequency. And so the result of this is that you do this again, you do it for the whole observation and build up your data sets, but the result of this is you end up receiving lots and lots of small data sets in both field of view and their physical size, physical disk size, which are at different positions across your primary beam. And this is a stupidly parallelizable method, and it greatly simplifies all of the aforementioned issues. So remember, your W term gets larger as you go for larger images. This doesn't occur anymore because you're only going to make small images. You don't have to make huge image sizes, single image sizes anymore, because you've only got small images. You make lots and lots of small images. So this kind of saves you in the long run, and it's really easy. But the advantage as well is that the choice of these phase sensors is also up to the user. So you could set them so they cover the entire primary beam, which if it's 99.99% noise, why would you do that? Or you could just do it with some sources of some sources of interest. So say if you've already got a VLA observation of the field, then you could just select those VLA sources, because if there's a VLA source, it's more likely there's going to be a VLBI source, just because how point sources work on all spatial scales. So this is kind of the method which is done nowadays, and in the next steps I'm going to talk about kind of the different calibration steps which we have to do slightly differently because of the way this data is set up. And this calibrating wide field VLBI data is much easier than you think, and I'm just going to do a disclaimer that the next bunch of slides is not a shameless self-promotion of everything that I've done. It's just simply that not many people do wide field VLBI anymore, or do wide field VLBI full stop. But what I'm going to try and convince you guys today is that it's not much different to standard VLBI calibration, and also some of these techniques will have some relevance to if you just care about one source of the pointing center of your array. So there's kind of three areas that are different from standard VLBI data processing. There's how we apply solutions when we do phase referencing. There's a bit on self-calibration, so I'll kind of extrapolate on what Javier has said this morning. And then, of course, there's the big one, which is primary beam corrections. But on top of this, I just want to point out that there's loads of pipelines that are now developed. So Michael Janssen will talk about this tomorrow, but the ARPA-CAR pipeline is very, very good. But there's also other ones in development on top. There's my own, which I'm going to plug in a minute, and also the EVN CASA pipeline, which Ilse spoke about yesterday. And this can make your calibration much, much easier. So I'm just going to have a slide on a shameless plug. I'm really sorry. But as part of the wide field surveys I've been involved in, we have our own centimeter VLBI pipeline. It's built so it's modular. So if you want to use ARPA-CAR to do the fringe fitting, because it's much better at doing fringe fitting than this one, then you can use that, and then use this centimeter VLBI pipeline to do all the wide field VLBI extra things. And this pipeline, will do all the a priori EVM, VLA, VLBA data stuff, and it's all in parallel through CASA-MPI. But it also has kind of support for use on HPC clusters, which are controlled by SLIM or PBS Pro, and also if they use Singularity, it will also support this. But it's also usable on your local machines too. At the moment, it's just me that's been using it because I only built it a few months ago, but it does need some testers if you want to have a go with it. And it's just to let you know, it's built for wide field surveys, but the direction independent calibration at least works for normal data, at least for continuum data. And there's lots of other things which I'll describe in the next few slides, like the primary beam correction schemes, the multi-source self-calibration, and how we automate selecting the parameters, which I won't talk about in this talk. So that's just my shameless plug, I'm sorry. I'll get back to the talk. So with calibrating wide field VLBI data, typically what you're going to have is one of these phase sensors in your beam will have the phase, bandpass, and fringe finders attached. This, of course, remember, these data sets are about a few gigabytes each. But the most important thing is that for every phase sensor that you get, it may be thousands of phase sensors, your standard VLBI calibration applies. So you can derive all of your calibration onto this single phase referencing, this single phase center. And then you can take these calibration tables and all of your flagging tables that are derived, and you can apply these to all the other target fields, kind of like this. Okay, and you've gone from doing a very small data set, which is a few gigabytes in size, fully calibrating it, and then you've just calibrated terabytes of data and an entire primary beam in VLBI. This, of course, is easily parallelizable because these same calibration solutions work for all of the phase centers. And at least in the pipeline that I have, this is implemented using CASA-VLBI, so it should be compatible with how CASA works at the moment. Now, on top of this is kind of the first difference between wide field VLBI data, but the second one goes on the lines of self-calibrating. And so let's take these three telescopes here. We've got some very short baselines here, and these telescopes kind of look through the same patch of the atmosphere. But when you get to VLBI baselines, your corruption due to the atmosphere, whether it's the troposphere or ionosphere, depending on what frequency you're observing at, will now be uncorrelated. So, you know, these effects are more severe. And often, again, these effects can also be uncorrelated at different locations within the target field. People who do LOFAR definitely know about this. So, you know, in order for us to be able to remove these contributions, we have to do self-calibration, as Javier has shown. But one of the issues that you have is that the number density of VLBI sources and their corresponding flux densities, you know, because you resolve out flux, you don't pick up all the fluffy emission, the fluffy jets in VLBI, means that sometimes you may not have enough signal to noise to be able to self-calibrate your target field. So there's kind of two ways which we get around this. Solution number one by Joan Roble and Mike Garrett, definitely used this in the early 2000s, is that it's called in-beam phase referencing. And essentially what you do is you just put a phase sensor on some very, very bright VLBI detection in the target field, as is shown by the little diagram below. And then you use this to derive the self-calibration solutions. And you know, you then apply all these solutions to the other phase centers, like this. Ta-da. So, you know, this works if you have a bright enough target field source. Of course, you're never going to have that all the time. So instead, myself and Enno Middelberg developed the multi-source self-calibration technique. And similar to the way that if you did a VLA image of an entire field, you'd use the model from multiple sources to do your self-calibration solutions. This kind of takes advantage of the multiple phase center correlation method to be able to do self-calibration solutions by combining all of the flux that you get in all the VLBI detections you get in your field. So how does this currently work? So, you know, we have our VLBI detections down here, these blue sources, which we've just found through some source finder. We take these VLBI detections and we copy them, we move them, and then we divide the model that we get through clean for each of them by the visibility. So you end up with an approximate 1 Jansky point source, and then we stack these together. So they're all approximately 1 Jansky point source, and you stack them together. And then you end up with something which is much higher signal to noise and is consistent with with a normalized point source. You then, you know, derive your self-calibration solutions using this. And once you derive your self-calibration solutions, you can then apply all these self-calibration solutions back to all the other phase centers. And then you can image these phase centers again and repeat them if necessary. And one thing you may find, for example, is that one of these phase centers now shows a source that can then be used in this multi-source self-calibration. And the one thing to say about this is actually, if you care about, oh, what's this going to do to my astrometry, the multi-source self-cal at least preserves relative astrometry in your field. And that's been proven. You can see the review by Maria Rioja about this. And so just to show what it does, this is from the Goods North field on a single source. And with standard phase referencing, this is our source on the left, we end up with a kind of low signal to noise. It's about 900 microjansky peak with some very, very, very non-Gaussian noise behind it, with just a signal to noise of 43. So that's just the peak, the RMS times divided through by the peak flux. But when we use multi-source self-cal, our noise characteristics look a lot better. There's less of these big negatives as we see in the other image. And our source flux density is dramatically increased. So we've now got signal to noises of over 100. Now, at least for implementing this code, it's available in apes via a Parser script from on my GitHub. But it's also about to be implemented into CASA as well. It's currently being tested. I wouldn't advise you to use it just yet until I've tested it. Now, this is where all the people who are currently asleep watching this, because they only care about the center of their primary beam, should start listening up, because multi-source self-cal at least can be used not just for wide field VLBI data sets. So again, your standard VLBI will normally just target some central field of view in the center. This may not provide enough signal to noise for self-calibration, especially if you don't know what the VLBI structure looks like. But often there's going to be more radio sources in the field of view. You may have a VLA image of the field. You just do a wide field image. Oh, and look, hey, there's a giant source here. There's a really powerful point source here. And so what you could do is you could then use the multiple phase center correlation, as is shown here, this source in the center that you care about, to target these bright sources. And even though you may not know what's there in terms of the VLBI flux density, you may just get enough signal to noise to be able to self-calibrate your data set. Plus on top, you may find something interesting. Wow, there's a binary supermassive black hole just sat there. And indeed, we've done this in real EVN data. So, well, EVN observations, they haven't been calibrated yet. And this is just a giant radio galaxy, ESO 422, as seen by ATCA, which is our background here. And then we wanted to use the EVN plus eMerlin to try and see how the fine structure of this jet in the core is, essentially. But on top of this, we didn't know how bright the VLBI source will be in the core, because you don't know how much flux is going to get resolved out. So instead, we also dropped a couple of phase sensors on these bright ATCA point sources, which may just give us enough flux to be able to do self-calibration. So that's kind of the second difference that we have for wide field VLBI, and I hope I don't scare you now with maths. But the kind of final problem, or I like to call it the final frontier, as I did in my cheesy proposal for this, is the primary beam problem. And the primary beam problems have been solved, or mostly solved, for all of your nice homogeneous arrays like Meerkat and partially ALMA and the VLA. But primary beams are essentially our most ubiquitous direction-dependent effect that affects every single radio observation. And so I'm just going to focus you back to the rhyme that Mark first introduced. And so if we just have two antennas P and Q, the visibilities that are measured is just the 2D, well, approximately the 2D Fourier transform of your sky brightness distribution. But then on top of this, you also have these extra corrupting effects. So these are the G terms here, what we call direction independent effects. So these are the ones which are based in your telescope, has no real dependence on where you're looking in your target field. So things like the bandpass, your complex gate areas can be approximated as direction independent. But then on top of this, we have direction dependent effects. And the primary beam is one of these direction dependent effects. And you can see that this sits inside this Fourier transform integral. So if you invert it, you've also got to somehow deal with these corrupting effects as well. And what we will show in the next slides is that this is kind of a more problem for heterogeneous arrays, which is mostly VLBI arrays. And that's mainly why this hasn't been dealt with too much, because no one did wide field VLBI surveys, nor did they care it was. And most of these are heterogeneous arrays, like the EVN, the LBA, etc. So for homogeneous arrays like the VLBA, the VLA, Meerkat, etc., the standard assumption that you would do, I'm going to ignore everything to do with phase issues. I'm going to ignore the blockages and the side lobe structure. You can go and read up papers on this. I'm just looking at the primary lobe. And so, the standard assumption here is that your primary beam for each telescope is identical. So EPEQ equals E for all of your antennas. And this is generally not varying with time. It does when you have side lobes and it rotates through, or squints and things like this. But in a simple terms, this basically means that each baseline observes the same apparent brightness distribution. And that is key for anything that you do with standard imaging. So your standard imaging algorithms, when you invert this equation to recover your B term here, assumes that each baseline observes the same apparent brightness distribution or a common sky. And then due to this, you can then invert your baselines to form the UV plane. And so in this case, the apparent sky is the same for every single antenna. And so when you end up inverting this, equation, you just recover B app here. And you can then just divide this through by the primary beam response in L and M in the image plane to recover what your true sky brightness is. This, of course, is not true with this rotation effect, but it can be approximately true. And so any images generated will be the brightness attenuated by a power beam. So the true source flux density will be recovered by dividing the image by the power beam response. So on the right here, we've got a nice image of the Goods North field as seen by the VLA. And then we just apply the power beam, and you end up with the noise increasing on the outside along with the flux, and no real change in kind of the image fidelity of each of the sources here. Now, when we go to heterogeneous arrays, which is kind of what we're trying to solve just at the moment, the big issue comes from the following: is the fact that your apparent sky that you see, these E terms, which correspond to your primary beam voltages, are not the same for all your telescopes. If you have a 76-meter telescope, it's going to have a different voltage pattern to a 25-meter telescope. And so this is key, is that each baseline now does not observe the apparent baseline distribution. And if this happens, it manifests as some direction dependent, but antenna independent and dominant amplitude error. And so you can see this in the right-hand plot where we've got the VLBA, which is a homogeneous array, plus the Green Bank telescope, which is a 100-meter telescope in comparison. And Noela Herrera-Ruiz in 2018 essentially moved this telescope around, getting further and further away from this bright source in the center, 3C84. And you can see in the APES plot, so go get an APES plot in, you can see that this occurs as some amplitude error, which is proportional to the distance from this source. And so if you try to invert this, this would be some horrible, horrible amplitude error in your data. And so we can show this kind of more drastically, again, through some simulations. And this can drastically affect what achievable dynamic range you can get, especially very close to the face, the pointing center where your telescopes are pointing to. And below, for example, we've got a simple simulation of an E-Merlin array where we've approximated the primary beams as being homogeneous and the same, and an E-Merlin-B array which has 2 telescope sizes. And these are observing some point source with a fixed dynamic range above what the nominal sensitivity is of about 1,000. And you can see that with the E-Merlin-A array, as we get further and further from the offset from the pointing center where your telescopes are pointing, there's no real change because they're homogeneous. You just get adjusted by this the primary beam amplitudes, all the same, so it doesn't do anything. But when you get to the Merlin-B array, you start seeing these amplitude errors coming out further and further as you move further down the primary beam. And so these will effectively, destroy any image quality of sources that you're looking at, and also sources nearby. And we showed this with also, very, very heterogeneous arrays, so EVN arrays here, and you can see as we go from E-Merlin-A to EVN-B, the number of different antennas changes. And you can see here, for example, on the top, we've got the peak brightness when you don't have primary beam correction, and the peak brightness when you do have primary beam correction. And this is just the primary beam shape, of course. But now we've got the actual noise in the images, and you can see there's no change in the noise essentially for E-Merlin-A, but we get a change in the noise because of this amplitude error for all of our heterogeneous arrays. And this is effectively shown down here with the ratio of the dynamic ranges too. And even at the EVN, when you get a couple of arc minutes away, you get a drastic change in your dynamic range. But what's worth saying is that these errors are proportional to your source dynamic range. So if you have a very low signal to noise source, it's not going to affect it so much. It's a multiplicative effect. Now, these effects are going to be much more important when we start increasing our VLBI bandwidths, plus also the inclusion of kind of phased up elements such as the Meerkat and SKA. Now, to correct for this effect, we need to do models of the primary beams, something which, the EVM will hate me for saying this half the time, but this is kind of the current status of the current primary beam models. And at least for the VLBA and GBT, there's some estimates for how big the beams are and what they look like. This is the same for eMerlin. But for the EVN, at least, this is all about to change. It's been a while. There's kind of an EVN plus eMerlin joint effort to map the EVN stations and also provide independent measurements of eMerlin stations. And on the right just kind of shows our methodology from the proposal, showing that we'll take our EVN array and move it at these various different distances from some bright source in the center. And then in principle, we should be able to track how the beams look like with distance from the pointing center. Now, at least at the moment, the current primary beam models are kind of 1 to 2 gigahertz, which is where you do wide-field generally, are pretty crude estimates. So luckily, hopefully in the middle of next year, we'll have some nice, beautiful primary beams for you guys to try. So kind of the final part before I run out of breath is what are the ways which we can correct for the primary beams. So with our primary beam models or approximations at hand, how do we apply these corrections to heterogeneous arrays and wide-field VLBI data? So there's kind of currently image plane correction, which you do for homogeneous arrays. There's something which I've called differential or stepwise primary beam correction, which is the standard way we'd normally do it. And then there's also the new way of doing UV plane correction via A projection. So if you're going to do it in the image plane, then you calculate your total power beam by just taking kind of the average weighted sum of all the baseline beams, which is just the average of the voltages of the two telescopes that make up that baseline. So this is our voltage of antenna P and our voltage of antenna Q. And then you would just divide this subsequent image by the total power beam. So the weighted sum of all these baseline beams is the weights down here. Now this, is fine for our homogeneous arrays. It provides just some scalar shift in the image plane to fix your flux scaling. But it does not correct for your direction-dependent, antenna-independent errors that we've seen earlier. So, it won't fix this error that we saw when we were looking at this heterogeneous array. Now, in principle, you can fix some of these amplitude errors via self-calibration, but if your source isn't strong enough, you can't. So the second way is that we use what we call differential or stepwise primary beam correction. And because we've got our multiple phase sensors at different parts in the primary beam, we can then use just a singular gain table which corrects for your primary beam attenuation at the center of that phase center. So this is kind of what I've been saying here at the start, which is correct each phase center in the UV plane using a gain table with some singular value of each antenna's primary beam voltage, which you then evaluate at the center of the phase center. Okay, and so this effectively removes these E terms at the center of the phase center in the UV plane. So this will remove those horrible amplitude errors. And then occasionally outside of these phase centers, because it's kind of just for the phase center, you would calculate the error difference between what the real primary beam response is and the UV corrected response for any sources away from the phase center. But this is, so kind of note that this kind of only perfectly corrects your amplitude errors at the center of each phase center. So it's not perfect, but it does a pretty good job. And any residual amplitude errors that are left in your data are much, much smaller than the image plane only correction. And these are proportional to the slope of your primary beam response, the distance from the center of the phase center, and any primary beam model errors that you may have. And so here's kind of an example. I've simulated a 12-hour EVN observation, and I've, Oh, okay. I've simulated a 12-hour EVN observation, and these are our phase sensors, these Cayenne points over here, and in the background is the primary beam response. And when we do the primary beam correction in this method, we end up with kind of this fly's eye image where your primary beam correction is correct for the center, but as you move to the edge of the phase centers, you get some error, some residual amplitude error in there. And so this method is the current way which is used in wide field studies. At least in apes, there's a task called CASA-VLBI, which you can do it for the VLBA and GBT. And then for the EVN, you can either use the script that I made, or you can use what the EVN pipeline output does, at least for the new data sets. And so at least for this method, the kind of CASA conversions, again, are currently being tested. And just to show this kind of primary beam correction in action, this is from my 2018 paper at the Goods North, where this is the Effelsberg primary beam, and we used some crude estimates of primary beam models in order to accurately correct for partially accurately correct for the primary beam response. So the final way in which we can, remove all the errors as long as we have perfect beam models is to do a projection. And this corrects for the primary beam response as we grid our visibilities. And at the moment, this is implemented in what we call the image domain gridder method, which is part of the WS clean package, so not part of CASA. And this corrects for the primary beam effects with much smaller errors than the other methods. So on the right-hand side, we've got the A projection kernels. So these are our voltage responses of our various telescopes. This is the Effelsberg 100-meter telescope, TMR, Jodrell Bank, which are bigger. You can see their attenuation. And then we can use these models to then give us a lovely, smooth RMS map of our target field. And if you have perfect beams, you get perfect corrections. Well, possibly. But the advantage of using this method as well is that we can also implement more complex beams. So you can do some true frequency dependence. You can do the rotation of the beams due to the mounts and the parallaxic angle. But also, this method can do other direction-dependent effects, such as pointing errors, tech dispersion across your field of view, which in principle can be calibrated this way. And so just to kind of note, all of these kind of correction schemes will be easy for the user to use and is planned in this VLBI pipeline. But crucially, this is not native to CASA. So with all of these advancements put together, wide field surveys in VLBI have come a long way. This is an example from the Goods North field, one of my favorite fields in the world, and this is Mike Garrett's, where there's in the center, we've got the KPNO optical image in the background with the Westerbork synthesis radio telescope on top as the contours. And then there was a VLBI survey with the EVN, and there was kind of 2.5 detections here. And as we go, more into the future, the techniques came along. We had Chi in 2013, which was observed in 2004, which, looking at the same field, now detected 12 VLBI sources, and then now we're looking at tens of sources in a single pointing. This is from my 2018 paper, which saw 31 sources, and half of these sources aren't even in the field of view of the original WSLT and KPNO image. So my kind of key takeaways just for the last minute is that wide field VLBI has many use cases, and if you have other things it might be useful for, then go for it. The initial calibration is very simple. Everything is easily parallelized and it's becoming user-friendly. Some of the calibration techniques that I've outlined are applicable to standard VLBI observations, so like the multi-source self-cal, for example. And at least, at least for the moment, the final hurdle of primary beam corrections is currently being overcome. And you guys can use this for your future wide field VLBI needs. So thank you very much.
Thanks, Jack. That was a very interesting presentation. I'm glad to see that the primary beam correction for the EVN telescopes is finally getting handled properly. There's already some questions popping in. If you have any more, feel free to start posting in the Q&A or in the MetaMost channel number 10, wide field imaging. I'll hand over the floor to Ivan, who is our question master for this afternoon.
So yeah, at the moment, there are 2 questions in the Q&A at Zoom. So the first of them is from Sumit, who asks, in the pipeline to make wide field imaging, what parameters are required? So how much information you need to configure the wide field imaging? Is it automatic or requires some manual intervention?
In principle, at the moment, it's manual, but in principle, there's at least code behind the scenes at the moment, which would take your UV coverage and work out what the standard parameters are that you would need to make the image. The key thing for it that maybe I didn't say properly is that with wide-field VLBI, you've got these multiple phase centers, so you're just making little images which aren't necessarily mosaicked into your 300,000K by 300,000K image, because that would be silly. So yeah, so at least for the pipeline, it will be automatic.
Okay, well, did this answer the question, or maybe Sumit has?
Yeah, he can follow up if there's more questions, or if it wasn't clear. But I would like to add one thing, which I found is always a bit confusing, especially for people coming from the ALMA side. They are used to doing mosaics, which actually images the entire primary beam. In VLBI, as Jack pointed out, we only do small subsections of the entire primary beam, because most of the area you're looking at is noise. You don't need to image the noise. You only image the parts where you know there's a source.
Mm-hmm. Yeah, well, there's another question from Yoon, who asks, for multi-source phase calibration, how densely the phase centers should be sampled for the decent primary beam correction?
So the multi-source phase calibration is not necessarily for primary beam correction. Primary beam correction is just depending on what telescopes are in your array. If you're talking about, yeah, I guess that's kind of answered it maybe, but yeah, so it's kind of, maybe there's a little bit of confusion that the multi-source phase calibration is not for primary beam correction per se. So normally you would apply your primary beam correction before you do any self-calibration of your target field. So you want to remove those amplitude errors straight off, and that is done just by knowing what the primary beams look like, which you can get, from the observatory, or you will be able to get from the observatory.
Okay. So yeah, it's actually quite subtle to disentangle what would be the phase correction, and then but you also need amplitude correction. We are far from the phase center. It's a little bit confusing. Yeah. So if we move to the Mattermost, there has been some interaction already. So Yoon was asking what field size we were talking about. And there has been an answer from Benito, who says that roughly producing imaginary place within a primary beam of the telescope arc minutes at gigahertz frequencies. So that would be the order of magnitude, let's say, of the primary beams. But these would not imply a single image with that field, but a smaller individual images centered at different places within that range, which is what Ilse was noticing actually. So, and then Yoon was asking again, is this multiple phase center correlation so-called direction-dependent calibration? Oh, he said the question was addressed already, but okay, if you want to elaborate on that, that would be.
In principle, the multi-source self-calibration is not direction-dependent. It works the same way as if you did self-cal on your field. It has one advantage that it retains relative astrometry. But in principle, there is at least one of my colleagues here is making a direction-dependent version, which then will just group the sources in different parts of your primary beam, and then make some phase screens. So you interpolate your solutions across your primary beam, and then it, in effect, becomes direction-dependent. But yeah, the multi-source self-cal just acts as a way to increase your signal to noise available to do standard self-calibration on your target field.
Mm-hmm. Yeah, then there has been some comments from Perez Torres about the primary beam of the EVN, which goes in the line of the fact that the EVN is quite heterogeneous, okay? Because he was telling that, yeah, for Effelsberg, for instance, which is the largest disk, one gets rather small values, but for the rest of the antennas, EVN is very homogeneous. So how you compute the primary beam for EVN experiments, which is what you have addressed actually in the last slides. And then Perez Torres says in slide 19 Okay, yeah, so Pedro has just posted something else. So it looks like the peak to the right in slide 19. So if you could go back to that one.
Yeah.
The peak, it seems that the peak to the right is much higher than the peak to the left. So an SNR increment should come up from decreasing RMS noise rather than increasing the peak brightness, but which I think is the effect of correcting from the primary beam, right?
No, so yeah, the multi-cell self-calibration is just correcting for the phasing. So this is just you're pulling flux which has been scattered into the noise because of the atmosphere. This is not doing any primary beam stuff. So you're just pulling back the flux which has been scattered into the noise, which increases your signal's noise. So it's a combination of both decreasing the RMS and increasing the source peak.
Mm-hmm. Okay, so then Pedro Torres asks about the computational costs. So how costly is this correlation-wise to perform this wide field imaging?
Oh, I need Ard on here to answer this one.
You've
I think
Mark.
yes, Mark has said that he can answer to that. Yes.
So there's two issues here. There's a small additional cost per phase center. But Jack didn't say this, but he uses in these fields, he uses, well, 700-800 phase centers. So 700 times a small additional cost is still a significant cost. These big ones really take us quite a bit of time to correlate, because the correlator is actually constrained by the amount of memory that we have and not by the amount of CPUs that are in it. So yes, correlating such an experiment can take up to a week, but adding a few phase centers to do the, what do you call it, Jack? The
multi-cell self-cal.
Yeah, multi-cell self-cal. That is almost free. So that's maybe a 30% cost, extra cost for correlating at higher spectral resolution, and then a small cost for each additional phase centers. But up to 10, that's almost nothing. So unless you want to really do these wide fields and have lots and lots of phase centers, you shouldn't hesitate to propose.
Oh, by the way, so Yun has just posted that the slide related to the comment about the primary beam was slide 32, where we were showing multiple phase center pointings. So the question was, how frequently do you sample to characterize the primary beam of the wide field?
Ah, I see. Okay.
So about this reading.
Yeah, so this is just an example to show how the stepwise primary beam correction happens. So the blue points are just example phase centers that you may give to the EVN. You don't want to do this because Mark and the EVN people will hate you for doing it. But yeah, so you just, with this method of primary beam correction, you just correct for the primary beam at the center of these phase centers. So you can imagine you're going to get for every pointer, you end up with a small data set. And then you just apply a gain table to that data set with the corrected, the primary beam response. And then you essentially end up with an RMS which is flat across, but you've just removed these horrible amplitude errors. So, whether you want to look at, doing the entire primary beam is very dependent on what the correlator people will average your data down to. So the distance between adjacent phase centers here is just dependent on how much averaging once the initial wide field correlation has happened, you then shift and then you average them down. And it depends how much that averaging goes down is by how separated you'd need to do these points in order to map the primary beam. So that's very much on the correlator side, and what you decide and they decide. It's very user dependent that way. But yeah, again, often you would never ever do this. You target VLA sources. You'd average down really, really heavily because you only care about a few arc seconds around that VLA source or low resolution source.
The idea is that if you do more averaging, you need to sample more closely the primary beam.
But yeah, again, you wouldn't ever cover the entire primary beam. This is just a kind of an example to show how the primary beam correction currently works.
May I ask some, or make a quick comment about the case of ALMA and the Atacama compact array? You know that there has been some discussion in the last years actually about what was better to do to combine the main array and the compact array data. So there was one opinion that was basically defending the combination in the image plane, because each one of the two arrays is homogeneous, but the two arrays themselves, they have different sizes. So correcting on the image plane, each one of them separately is trivial. Then you can just combine the images once they are corrected for the primary beam. But the other option was to combine them in Fourier space. And that's not trivial, because even though you have two disconnected arrays that are homogeneous themselves, then you have baseline dependent corrections that are different, in Fourier space. So how you would deal with this special case? Would it be would there be something that would be simplified in the analysis? The fact to have two arrays that are disconnected among themselves, but you combine them in Fourier space?
Yeah, I guess, well, I haven't really thought about it too much, but off the top of my head, it definitely helps the fact that, these are, all the baselines are between themselves. So at least the primary beam correction is pretty simple because you only have two models, and then you could use that for each one of those separately. Because the big issue, oh, sorry.
Because I was understanding what you were saying. So you don't have two E's to the direction independent corrections multiplied that are different, the measurement equation, because you don't have baselines from one array to the other. That's what. Yeah,
exactly. Yeah, it's those interconnecting baselines that are the big problem generally. But yeah, I guess you could do something like through the A projection method, but instead you just feed it two primary beams, which makes it much simpler.
Okay.
And at least this new image domain grid is really, for doing A projection, it's quite it's quite flexible. These kernels are just FITS files, so you just sample your model into the FITS file, and it's computationally expensive, but it's also accelerated by GPUs, so it actually is quite quick to do it.
GPU implementation, that's in CASA?
No, this is separate. It's part of, well, it's WS Clean.
Okay.
I think we have time for one short question, if there is anything left.
Well, yeah, I had the question, which is T-Clean claims to have an A projection implementation as well. Did you try using that one?
The issue is that I have no idea how to get. I've tried it for many years of how to get the primary beam models into CASA properly and for it to work properly. So whenever we've tried to get it to work within the VP package and then we compare it to using other packages, it's never what we expect it to be. And I don't know why. That's the best way to describe it.
Actually, I think I have a possible explanation, because I was also playing with this for the case of ALMA and the ACA, and it seems that there's some quantities hardwired to the code, so that even if you change the antenna table and provide the size of your telescopes and the definition of the primary beams and so on, CASA is stubborn and still keeps using the values that are hardwired, and they don't work for some reason.
That's interesting.
So if you provide the name of an observatory, they have some values which are hardwired there, and there's absolutely no way to override them.
Yeah, I think that's what we got to as well when we tried to put emailing into it.
Okay. There's one last question in the Q&A, but I think we can move on to Mattermost.
Yeah, I don't see anything else in the Mattermost,
Oh.
and no new. Is there anything new that I didn't get, or?
Not in the
No.
Mattermost.
Okay, so it seems that there's nothing added. So I think that's it for the question and answers.
Awesome.
Excellent.
Thanks a lot.
Oh, sorry. There's there's in the question and answer. There's a new one. Yeah, sorry for this. So Sumit is asking again if in an heterogeneous array primary beam of which station can be fully made. So the smallest antenna or the largest one?
If I wasn't constrained by correlators, I would say any of them. But but yeah, no, you would never want to do the entire primary beam. You just want to look for sources that are already there. So don't give the Jive correlator people headaches, because they already hate me. So they've had to redo the correlator twice, if I remember right, because of my project. So, but yeah, no. In principle, you can image as far as you want. You know, have a look at the Cosmos 2 gigahertz data, which goes all the way to the edge of the VLBA primary beams, targeting VLA sources out of there. Take a look at the M-Drive survey as well, which is the same. So, you know, you can use this technique in principle to map thousands of degrees in VLBI, but just make sure you pre-select those sources on something that's already there, unless you're mad and you want to search for stuff that's variable that's not going to appear in observations at a different time.
Okay, now I think that's it. Yeah.
Yeah,
Jack, thank you. It was fantastic talk. I really enjoyed it a lot.
There's a few more popping up in the Mattermost, but it's time to wrap up because we've got the next event coming up, which is our walk. And actually, we have a little bit more time for that because it's followed by the break. If you need instructions on how to register your step counts, they are all on the wiki page. And I will make a dedicated channel in the Mattermost as well for the books in case you have issues with signing up for the online system. Please do give that a try because it makes our life a lot easier. But if this for some reasons is blocked in your country or you have other issues with it, go and look for the dedicated channel which will appear in Mattermost in the next 10 minutes. We reconvene for the data processing session. Let me check at 4 o'clock UT. Here in the next plenary session, I will share the link also in the general channels. Thank you very much, Jack, for a very interesting talk. We're on all 4 our walks, and it's actually quite funny to realize that several people will be walking with me, but I will not be able to see you all until we get back here and share our images. So share pictures, let us know what you've been doing, and then we'll see you at 4 UT.
Okay, I'm going for the walk of Ilse. May I ask Jack a question? Since you are still here, but is it possible to do multi-frequency wide field? I mean, or would you choose a preferred frequency to do a wide field VLBI survey?
I think it's just dependent on your field of view, right? Because the primary beam scales as lambda over d. So if you did it, you could do it in 5 gigahertz, but you haven't got much area to search for. So it can be done at any frequency. It's just the lower the better if you want to go wide. But if you cared about other things in your field very close by, just drop a phase center on it. It should be fine.
Yeah, no, I was thinking of course, for the lensing science, which is not very efficient with the wide field, obviously, but just because it's a very small probability. But when you have multi-frequency information at the same time, you can already say this is a lens, this is not a lens. And so, of course, this has some issues to because of what you said. But okay, thanks a lot.
Yeah, no worries. All right, enjoy your walks. I'm going to drive home, so that's going to be my walk. See ya.
Ciao.
Bye. Okay, I'm gonna wrap up now the questions and say.
Good, excellent. Thanks, Ivan.
So what do I send them to Jack for them to revise for you to revise?
The ones that are still open in the Q&A, you can copy and paste them into the Mattermost channel and tag Jack to answer them there. But I think
okay, so I just copy paste them.
Yeah, you have to copy paste. I thought there was a way to save the Q&A, but there's only a way to save the chat functions.
Okay, yeah. So yeah, wait a moment so I can.
I'm not going anywhere. I'll leave it open for.
Because what Casey was doing yesterday, she wrote an answer and then she sent me an email to just to
yeah, Miguel, I was trying to write the answers. I thought that we had to write the answers, but
actually I was so I thought I should do the same.
But
okay,
you see, you're smarter than me.
I tried this morning to type the answer as the question was being answered live, which works in some cases, but if I don't quite understand the details, then it quickly deteriorates.
So yeah.
Yeah, well, that's why I checked. Ivan.
Sorry?
Putting them.
Sorry?
That's why I sent first my proposed answers to you to double check.
Okay, so in the end, I don't have to. So just
no, in the end, I think you don't need to answer them. You just copy them into the Mattermost and say, "Hey, Jack, answer it, please."
Okay. Okay. Good. Thank you.
Ilse, are you still there?
I'm still here.
So did you show this morning some distribution of the countries that, or are you saving that for last?
It's on the wiki page actually.
Oh, let me.
The tool that you suggested was actually quite pricey. So
it's free. No, sorry? No. Well, I thought it was free.
It is up to 25 people.
Okay.
And all these things, we looked into quite a few options for the polls and quizzes. And all these things are quite expensive if you want to do this in events of this size. So Olga found one which was a per event subscription. So we only buy it for this event, which was the cheapest option. But it was, it was somewhat of a nasty disappointment because you're not used to handling this many numbers of this.
Oh, I see the. So there's the map. Super nice.
Yes, if you click on it, you can actually zoom in and out. And
okay, and it shows the zip code.
Yes, I had to use data which were not under the GDPR protection, so I could only use zip codes and places for people.
Very nice to see that.
It's a really nice distribution. I was really happy with it. It would be interesting to see if we can map that onto the actual participants on the channels, but it seems we're roughly having about 50% of the people in the lectures.
But Ilse, I can't see Hawaii there.
You can or you can't?
No, it doesn't appear in the well, I can. No, I can't.
It is there. It's just really west of the United States. But there's something which is HY. So I think it's Hawaii.
Oh, I can no longer see the map because it's telling me I need to pay for it now.
Oops.
But the image is still there on the, that's a PNG image on the CASA wiki. That's what you get with all these things. Once you start using it extensively, people say, oh, now you have to pay for it.
That's weird because I can see it. I can, but if I look, here is Hawaii.
I don't know. I was just wondering whether there was somebody from there also, because I can see it in the wiki. Oh, by the way, Casey, I have uploaded the scripts that Miguel was asking yesterday.
Mm-hmm.
I realized that I was actually using a wide bandwidth, much wider than what I said. So I was using 1 gigahertz, and I said I was using half a gigahertz. So I have reduced to half a gigahertz. It improves a bit, and then I set the spectral index to -2 to just go back to wild. Okay, so the images will not be exactly the same as the ones I showed yesterday, but still it works.
Yeah. So you see, there's lots of people in Africa. There's lots of people in India.
India and Indonesia even.
Yes. Nobody from Japan on, or is no?
No, but the Japan is really pushing it in the time zones. I think this is at -10 or something. So they really hardly overlap with us.
Yeah, and more northern than this, no.
No.
It could be, huh? There is institutes there.
Yeah, and even in Northern Europe there is. So.
Of course. So we have still also people from Australia.
One. Yeah.
Nobody in the South Pole Observatory.
Nope.
No, nobody in the South Pole Telescope. Or it should be more there. Oh, I'll stop with this. But it's very fun.
Yeah, it's fun to look
for having that.
And this was actually fairly simple to make as well. Just copy and paste the zip codes, and it generates this map.
Mm-hmm. And you do that for every day?
No, just for the full list of registrants. So it's everybody who registered online is on the map. And for the actual participants at this point, I'm not sure. I think Benito said he had some scripts to check, but I've not been following in too much detail who is present and who's not.
No, well, it's not to hound people down or anything.
No,
it's just fun to see with whom you are talking to at the moment.
Yes. Yeah. Now it would be interesting to note this, because we had some discussions before in the organizing committee whether we wanted to charge a registration fee to avoid people registering and then not showing up. But that was so much work to set this up, especially because people can't come here. They have to find a way to transfer money internationally. So we decided not to do that, but then you get quite a significant number of people who register and never show up. And I think that is around 50%.
50, because the first day they were